Nuclear fusion. We always hear about it, right? The energy of the stars, this kind of holy grail for clean power.
Limitless, clean power, yeah.
But the catch, for decades, has been this just enormous roadblock. The cost. I mean, we're not talking pocket change. It's a colossal investment up front.
Yeah, they call it the massive capital requirement, or sometimes the billion-dollar entry problem, just to get a proof of concept going.
Right.
And that's really why commercial fusion always felt so distant, perpetually 30 years away or whatever the number was.
Always just over the horizon.
But things are genuinely starting to shift now, especially with new material science.
Magnets, right.
Exactly, particularly in magnet tech. It means we might actually be able to skip building some of those massive, older-style prototypes. We can actually shrink the whole star-making machine.
Which changes the money and the timing.
Completely resets the equation, yeah.
Okay, so that's what we're digging into today. We're doing a deep dive into this accelerated race for fusion. We'll focus quite a bit on a company called Renaissance Fusion.
RF, yeah. A French startup.
Right, RF. They're aiming to get fusion onto the grid way sooner than people thought possible. So we'll unpack their approach, look at the physics they're using the Stellarator thing, and their business strategy.
It's a really interesting mix of cutting-edge science and, frankly, bold commercial moves.
And we'll definitely get into the Stellarator design itself and these high-temperature superconductors that seem key.
HTS, yep. They enable these smaller, high-field designs. But we also need to talk about the physics trade-offs. Because shrinking the reactor sounds great, but it brings its own set of pretty tough challenges.
Got it. So let's kick off with Renaissance Fusion itself, the player and the timeline.
Okay, so RF, founded in 2020. The founder is an Italian physicist, Francesco Volpe.
And the mission is big. Design, build, commercialize a reactor using stellarators, HTS, and also liquid metals.
That's their tech stack, yeah. Stellarator, HTS magnets, liquid metals inside. Their slogan is, well, it's not shy, we're building a superstar on Earth.
Okay, and the timeline matches the ambition, I gather.
Oh, absolutely. Volpe is predicting that RF, and maybe some other leading startups too, will build their first actual fusion reactor within 5 years. That's 5 years from, around now.
Wow. 5 years. And net electricity.
Aiming for net power within a decade, which, you compare that to the big public fusion projects.
Yeah.
Some have taken 40 years or more just to get to the construction phase.
It sounds almost unbelievable. So what tech makes Volpe so confident? How do they avoid needing that $1 billion right now?
Well, that's where their commercial strategy is honestly quite clever. It's a two-pronged thing.
Okay.
They are a fusion company, that's the end goal. But at the same time, they're operating as a manufacturer of these high-temperature superconductor magnets, the HTS magnets.
So they sell the components before the reactor's even built.
Exactly. They realized these advanced HTS magnets are really needed today in totally different industries. Think massive offshore wind turbines or advanced MRI machines for medical imaging.
Okay, so they make money now?
They make money now, yes, which funds the R&D. But it does something else just as important.
Which is?
Technical validation. It proves to investors and to themselves that they can reliably make these complex magnets at scale, that the magnets work under demanding conditions. It de-risks the core hardware for the eventual reactor.
That is smart. So it's not just about the $60 million they've raised in grants and VC funding. It's proving the tech in the real world first.
Right. It builds credibility and solves the immediate cash flow problem.
And they're expanding geographically, too. Something about Italy.
Yeah, that's interesting. RF recently acquired a company in Pisa, Phymtech, and created Renaissance Fusion Italia.
Connecting back to the founder's roots.
Partly, but it seems strategic, too. It's being driven by plasma physicists Francesco Ceccarini and Laura Gagliotti there, with Diego Camarano as the Italian CEO. The idea is to build this tech bridge between France and Italy.
Bringing R&D back to Italy, specifically in fusion.
Seems like it. They're planning to hire quite a few people, over 20 engineers and physicists in Italy by the end of 2026. So it shows serious commitment, moving talent towards this Stellarator concept.
Okay, so the business model is clever, the funding is coming in, but like you said, the physics has to work.
Yeah.
Let's talk Stellarators. Why bet on that instead of the tokamak, which we hear about more often?
Good question. Tokamaks are definitely more common, think ITER. The Stellarators have this one huge potential advantage. Reliability, even if they are significantly harder to engineer.
That's the trade-off then. What makes them reliable?
Well, tokamaks need a really large electric current flowing inside the plasma itself to help hold everything stable. Stellarators don't. They use only external magnetic coils to create the entire confining field.
And these coils are complex.
Yeah. Think less like simple rings and more like incredibly intricate, twisted shapes wrapping around the whole reaction chamber, almost like a 3D sculpture.
That external control is the benefit.
That's the key. It means, in theory, they can run continuously, and crucially, they are immune to what are called major disruptions.
Disruptions. That's when the plasma collapses.
Exactly. Sudden, violent terminations of the plasma that can dump enormous energy onto the reactor wall in milliseconds. It's a massive concern for tokamaks. It can seriously damage the machine. Stellarators inherently avoid that failure mode.
Okay, so stability and continuous operation. But the engineering is tough, and that's where the superconductors come back in.
Right. To make the Stellarator powerful and compact enough to be commercially viable, you need very strong magnetic fields.
Yeah.
And that brings us back to the high-temperature superconductors. HTS.
The secret sauce, you call it.
Pretty much. HTS magnets can generate much stronger fields. We're talking above 10 Tesla on axis than the older conventional superconductors could manage.
Right.
This is core IP for RF. They've filed, I think, 11 patent families around HTS and liquid metals.
Ah, liquid metals. You mentioned that earlier. What's their role?
Safety. Safety and public perception, yeah. Fusion is already much cleaner than fission, less long-lived waste. But RF is tackling the perception issue head-on in the design. They plan to coat the inside wall of the reactor chamber with a thick layer of liquid metal.
Okay. What does that do?
It acts as a shield, basically. It absorbs neutrons, minimizes the activation of the structural materials behind it, reducing radioactivity. And, by designing that in from the start, they hope it boosts public confidence. It physically contains things better.
So it's a shield, a heat transfer medium maybe, and a public trust element. Clever. Yeah. And the target performance for this design, the HSR 418.
Ambitious. They're aiming for 3 gigawatts of fusion power with a fusion gain, Q, of 40.
Q of 40 meaning?
Meaning you get 40 times more energy out from the fusion reactions than you put in to heat the plasma. That's well into net energy territory. And you really need those strong HTS magnets to even think about hitting that kind of target in a reasonably sized machine.
Okay, so HTS magnets give the strength. Now let's get into that counterintuitive physics.
Yeah.
Using stronger magnets to actually shrink the device.
Right. This is where it gets really fascinating from a physics perspective. Historically, the path to fusion power seemed to be bigger is better, build larger and larger machines.
Like ITER.
But HTS flips that script. If you can massively increase the magnetic field strength, let's call it BOE, you can actually shrink the physical size of the reactor, the major radius R. There's a scaling law, approximately $3, Sim B34.
Okay, Sim B33. Let's unpack that. Stronger B means smaller R. How much smaller?
Significantly. It means if you can, say, double the magnetic field strength B, the required radius R shrinks by, more than half. It's not linear. HTS gives you that high B.
So you can skip the giant national lab scale facilities.
That's the promise. Build powerful gigawatt scale reactors that could, potentially fit inside a large factory building, not require a whole dedicated campus.
And the core physics seems to scale nicely too. The source mentioned things like plasma beta profile, thermal diffusivity. They stay pretty constant.
Yeah, that's one of the really elegant parts. As you scale down the size R and scale up the field B along that Sim B34 curve, a lot of the fundamental plasma physics parameters, when properly normalized, stay remarkably similar. The optimization problem for stability, for transport, for keeping energetic particles confined, it doesn't fundamentally change that much whether the machine is 7 meters or 22 meters in radius if you scale B correctly.
Okay, but there's always a but.
There's always a but. The plasma physics might be manageable, but the engineering challenges get way, way tougher as you shrink the reactor.
How so?
The biggest one is something called the neutron wall load, NWL.
Okay, neutron wall load. That's the intensity of neutrons hitting the inner wall.
Exactly. How many high-energy neutrons smack into each square meter of the wall per second? When you shrink the reactor, say down to that 7-meter radius example, you still have roughly the same total number of neutrons being produced by the fusion reactions.
But a much smaller surface area for them to hit.
Precisely. So the neutrons are far more concentrated. The NWL goes through the roof. The paper mentions values around 7.32 megawatts per square meter for a compact R7 meter design.
And that's bad.
That's extremely challenging because current materials planned for reactor walls, like this steel called Eurofur, they have limits on how much neutron damage they can take before they become brittle. This damage is measured in dPA displacements per atom.
Okay, dPA is like a damage counter for the material.
Kind of, yeah. And Eurofur is currently only qualified up to about 20 dPA. With an NWL of over 7 mTOE2 down, you hit that 20 dPA limit very, very quickly.
Meaning you'd have to replace the inner wall constantly.
It severely complicates maintenance, replacement of the tritium breeding blanket components, and the overall lifetime of the reactor structure. It's a huge material science and remote handling challenge.
And there was another issue with small reactors. Something about the blankets.
Right. The components inside the magnet, specifically the tritium breeding blanket and the neutron shield, they need to be a certain minimum thickness to do their job. Roughly 1.3 meters combined, let's say.
Okay, a fixed thickness.
A fixed thickness. Now, in a really big reactor, that 1.3 meters is a relatively small fraction of the space between the plasma and the magnets. But in a compact 7-meter reactor, that 1.3 meters eats up proportionally much more of the available space.
Pushing the magnets further out.
Exactly. It forces the complex magnetic coils to be positioned further away from the plasma edge than you'd ideally want. And to maintain the required magnetic field precision from further away, the coils themselves have to become exponentially more complex and difficult to design and build.
Wow, okay. So shrinking the reactor simplifies the scale, but complicates the engineering intensely. How do they manage that? The sources mentioned over-engineering the field.
Yeah, that's a clever strategy they explore. Instead of just designing the magnetic field B to be exactly strong enough to hit your target Q40, you deliberately make it even stronger.
Stronger than needed. Wow.
Let's take their example. A 13.5-meter radius device. They calculate the B needed for Q40. Then they consider increasing that B by, say, 25%. Now, that would normally produce way too much fusion power.
Right.
But you can then bring the power back down to the target 3 GW level by adjusting the fuel mix. Specifically, you use less tritium and more deuterium. You change the DT ratio.
Okay, so you overbuild the magnet strength, then dial back the fuel potency. What's the benefit?
Several benefits, actually. It lowers the required plasma beta, that's the ratio of plasma pressure to magnetic pressure, which is good for stability. It also lowers the pressure from the fusion alpha particles, but maybe the biggest win.
Yes.
It significantly increases the tritium burnup fraction, maybe up to 3 times higher.
Meaning you use the tritium fuel much more efficiently?
Much more efficiently. You get more bang for your buck from the tritium you put in. This eases the requirements on the tritium breeding blanket and the whole fuel cycle, which is a huge deal, especially in a compact machine where breeding tritium efficiently is already hard.
So over-engineering the field buys you margin on the fuel cycle and stability. That's a really interesting trade-off.
It is. It shows how interconnected all these design choices are.
Definitely a complex puzzle. So let's try and synthesize this. The goal is crystal clear, limitless, clean power.
Right. And companies like Renaissance Fusion are making a big bet that this Stellarator HTS path, combined with clever engineering and business strategies, can get us to commercial fusion maybe in the early 2030s.
Which, if it works, what does that mean for you, listening? It means a potential future with a stable, clean power source. One that could handle the massive electricity demands of, say, a fully electrified transportation system or heavy industry.
It could fundamentally change energy economics, grid stability, you name it. The impact would be profound.
But there's a final thought here, a challenge, really.
Yeah, the sources strongly suggest that while the plasma physics of confinement seems to be getting clearer, especially with HTS enabling these high fields,
the real bottleneck might be shifting.
Exactly. The future might hinge less on figuring out the plasma itself and more on whether we can rapidly innovate the materials science and structural engineering. Can we build components, walls, blankets, magnets that can actually survive and be maintained in that incredibly harsh, high-neutron environment of a compact, powerful reactor?
Especially with those daunting neutron wall loads we talked about.
Precisely. Dealing with over 7 OMA WM22, that requires breakthroughs. Maybe things like liquid breeders, like molten salts circulating through the blanket, or designing magnets that can be taken apart more easily demountable coils for faster maintenance. That engineering challenge, managing the sheer power density, might be the critical path forward now.
Something for you to definitely think about and watch. The engineering solutions needed for that extreme environment.
It's where a lot of the innovation needs to happen next.
Well, thank you for joining us on this deep dive into the fast-moving world of fusion energy and the strategies trying to accelerate its arrival. We'll keep tracking it.